Following is a presentation on ferroelectrics presented by IEEE's Ultrasonics, Ferroelectrics, and Frequency Controls Society and the University of Houston. This presentation will cover what are ferroelectrics, what are the properties of ferroelectrics, what's the classification of ferroelectrics, and what's the application of ferroelectrics. Ferroelectrics are materials which possess a spontaneous electric polarization, known as P of S, which can be reversed by applying a suitable electric field, such as E. This process is known as switching and is followed by hysteresis. Ferroelectrics are electrical analogs of ferromagnetics. Ferroelectrics. The internal electric polarization is physically tied to the material lattice. Any change of the physical lattice will change the electrical characteristics and generate a current even without an external voltage applied. Two stimuli can change the lattice dimensions of a material: force and temperature. The generation of a current in response to the application of force is called piezoelectricity. The generation of current in response to a change in temperature is called pyroelectricity. A few ferroelectric properties are that most ferroelectric materials undergo a structural phase transition from a high-temperature non-ferroelectric or paraelectric phase to a low-temperature ferroelectric phase. The paraelectric phase may be a piezoelectric or non-piezoelectric and is rarely polar. The symmetry of the ferroelectric phase is always lower than the symmetry of the paraelectric phase. The temperature of the phase transition is called the Curie point, T sub C. Above the Curie point, the dielectric permittivity falls off with temperature according to the Curie-Weiss law. In this law, C is the Curie constant, T sub 0, or T sub 0 should be less than T sub C, is the Curie-Weiss temperature. Some ferroelectrics, such as barium titanate, undergo several phase transitions into successive ferroelectric phases. Barium titanate has a paraelectric cubic phase above its Curie point of about 130 degrees Celsius. In the temperature range of 130 degrees Celsius to 0 degrees Celsius, there is a ferroelectric tetragonal phase, where an axial ratio of 1.01 is stable. The spontaneous polarization is along the 001 direction in the original cubic structure. Between 0 degrees and negative 90 degrees Celsius, the ferroelectric orthorhombic phase is stable, with polarization along the 111 direction in the original cubic structure. Temperature below negative 90 degrees C, the phase transition from orthorhombic to ferroelectric rhombohedral phase leads to polarization along the 111 cubic direction. The following is the phase transition sequence for barium titanate, going from cubic to tetragonal to orthorhombic and rhombohedral. All ferroelectric materials have a transition temperature called the Curie point, denoted as T sub C. At a temperature greater than T sub C, the crystal does not exhibit ferroelectricity, while for a temperature of less than T sub C, it is ferroelectric. Decreasing the temperature through the Curie point, a ferroelectric crystal undergoes a phase transition from a non-ferroelectric phase to a ferroelectric phase. If there are more than one ferroelectric phases, the temperature at which the crystal transforms from one phase to another is called the transition temperature. For example, the relative permittivity varies with temperature as barium titanate crystal is cooled from its paraelectric cubic phase to the ferroelectric tetragonal, then the orthorhombic and rhombohedral phases. Near the Curie point, or transition temperature, thermodynamic properties, including dielectric, elastic, optical, and thermal constants, show an anomalous behavior. This is due to the distortion in the crystal as the phase structure changes. Ferroelectric domains. As previously described, pyroelectric crystals show a spontaneous polarization denoted as P sub S over a certain temperature range. If the magnitude and direction of P sub S can be reversed by an external electric field, then such crystals are said to show ferroelectric behavior. Hence, all single crystals and ceramics which show ferroelectric behavior are pyroelectric, but not vice versa. For example, tourmaline shows pyroelectricity, but is not ferroelectric. The following chart on domain wall movement shows the relationship between polarization and voltage for ferroelectrics. The most important characteristic of ferroelectric materials is polarization reversal, or switching, by an electric field. One consequence of the domain wall switching in ferroelectric materials is the occurrence of the ferroelectric hysteresis loop, as shown to the right. The hysteresis loop can be observed experimentally by using the Sawyer-Tower circuit. As the strength of the electric field is increased, the polarization of domains with an unfavorable direction of polarization will start to switch the direction of their electric field, rapidly increasing the measured charge density. This can be seen in segment BC. The polarization response in this region is strongly nonlinear. Once all the domains are aligned, here at point C, the ferroelectricity behaves linearly. This can be seen in segment CD. If the field strength starts to decrease, some domains will backswitch, but at zero electric field the polarization can be seen as non-zero. This is at point E. The value of polarization at zero electric field, point E, is called the remnant polarization, which is described by P subscript R. To reach a zero polarization state, the electric field must be reversed. This can be seen at point F. The electric field necessary to bring the polarization to zero is called the coercive field, denoted as E subscript C. It should be mentioned that the coercive field, E subscript C, that is determined from the intercept of the hysteresis loop with the field axis is not an absolute threshold field. The spontaneous polarization, P subscript S, is usually taken as the intercept of the polarization axis with the extrapolated linear segment CD. Further increase in the electric field in the negative direction will cause a new alignment of dipoles and saturation. This can be seen at point G. The following video shows domain pinning in ferroelectrics by dislocation under low electric field along the hysteresis loop. There are several ways to classify ferroelectrics. They can be classified as crystal chemical, i.e. hydrogen bonded, or otherwise double oxides. Number of polarization directions, such as those with a single direction, or those with several equivalent directions, like barium titanate. Centrosymmetric nonpolar phases, such as Rochelle salts, that exhibit paraelectric phase above the Curie point, whereas barium titanate is centrosymmetric, and then the first versus second phase order change at the Curie point corresponding to the Curie constant. Here one group being of the order of 10 to the third Kelvin, and the other being of the order of 10 to the fifth Kelvin. Note, these four classifications do not necessarily coincide. Electroceramics are a particular type of ceramic valued for their electrical properties. These properties include the dielectric property, the piezoelectric property, the pyroelectric property, and the ferroelectric property. Some key facts about piezoelectricity include materials which acquire electric polarization under an external mechanical stress. This is called the direct effect. Materials that change size or shape when subjected to an external electric field, such as E. This is the converse effect. Many piezoelectric materials are not ferroelectric, but all ferroelectrics are piezoelectric. And above T sub 0, many ferroelectrics are still piezoelectric. The first part of this video explains the piezoelectric effect. Here we see that when the hammer hits the quartz cube, an electrical current is generated and passed on to the light bulb, lighting it up. Here we see the reverse piezoelectric effect. When a voltage is applied to the cube, it causes it to deform. The similar principle works inside a watch where a battery is applied to a quartz tuning fork, causing it to vibrate. pyroelectric effect is the spontaneous change in polarization with a change in temperature. It was discovered in 314 BC and named by Brewster in 1824. P is equal to the pyroelectric coefficient, which is a partial derivative of P subscript S with respect to time. Notice that barium titanate and TgS, like most crystals, have a negative pyroelectric coefficient. Heckman's diagram provides a visual representation of the relation between the thermal, electrical, and mechanical properties of crystals. In Heckman's diagram, the three outer corners are temperature, electric field, and stress. The three inner corners are entropy, electric displacement, and strain. Lines joining these corner pairs represent the principal effects. To further explain Heckman's diagram, we can see that coupled effects are the lines joining pairs not at the same corner. The bottom section represents the thermoelastic effects, the right side represents the electrothermal effects, and the left side represents the electromechanical effects. Several equations explaining these types of effects are shown below. Some equilibrium properties of crystals. An increase in temperature produces a change of entropy. As seen from the equation below, the change of entropy is a function of the heat capacity per unit volume divided by the absolute temperature. A small change of the electric field produces a change of the electric displacement. Here, electric displacement is a function of the electric field times the permittivity tensor. Also, a small change in stress produces a change in strain. Here, strain can be represented as a function of the elastic compliance times the change of stress. Some applications of ferroelectrics are in the use of reversible spontaneous polarization for the storage of binary data, usage of the piezoelectric effect for piezoelectric actuators and sonar detectors, and use of the pyroelectric effect for pyroelectric detectors for infrared detection, imaging, and thermometry.
FRAM, or Ferroelectric RAM, is a memory technology that combines the best of RAM and ROM. FRAM is ideal for smart cards, RFID, security, metering, and many other applications that require high-performance, non-volatile memory. What does it mean to say that FRAM combines the best of RAM and ROM? RAM, or random access memory, is fast but volatile. This means RAM needs a constant power supply to maintain data in memory. Examples are DRAM and SRAM. ROM, or read-only memory, does not need a power supply to keep data in memory. However, ROM is much slower than RAM. Examples are EEPROM and Flash. FRAM offers the best of both memory types. It is non-volatile and faster than conventional ROM. In fact, its performance is closer to RAM than to ROM. Here's how FRAM works. FRAM uses the dielectric film of a ferroelectric material as a capacitor to store data. PZT is used and placed between two electrodes in the form of a thin film. When an electric field is applied across the PZT cell structure, it polarizes the PZT compound. This polarization remains even after the electric field is removed. The compound moves along the hysteresis loop of the ferroelectric material to one of the two stable positions, as shown in the diagram. These two positions translate to data storage for binary zeros and ones in the memory cell structure. FRAM offers several major advantages over EEPROM and Flash, including its speed, endurance, low power consumption, security, and tolerance for radiation. Let's look at each advantage in detail. FRAM outperforms conventional non-volatile memory. In fact, it's about 30 times faster than EEPROM. One reason for this incredible performance is that FRAM overwrites the content in a single cycle. Also, the core of FRAM is at the CMOS voltage level, so it does not need a booster circuit, as does conventional non-volatile memory. This greatly increases FRAM's writing speed, reduces the stress on the ferroelectric material, and consumes less power. Here is a real-world demonstration of FRAM's superior performance. In this demo, FRAM, Flash, and EEPROM have been placed on a single board. The test uses the same data size and transfer rate for each memory type. As you can see, FRAM is significantly faster than either of the other two non-volatile memories. FRAM completes the test in half a second, compared to 2.9 seconds for Flash and a full 13.4 seconds for EEPROM to complete the same task. FRAM could run even faster, if not limited by the SPI transfer rate. FRAM's high performance is crucial for certain applications. For example, FRAM is used in transit cards, which need to quickly interact with the readers at the gate. In this application, data is read from the FRAM embedded on the card, security authentication and fare adjustments are made, and the updated data is written back to the card's FRAM memory, all in the blink of an eye. High-speed FRAM allows for faster transactions and improved traffic flow, enabling riders to move efficiently through the turnstiles even during busy rush hours. Another example is factory automation. In this case, a TV manufacturer does calibrations on a fast-moving assembly line. After the calibrations are done, related data, such as white balance and other information specific to each television, are quickly written to the FRAM-based storage within each TV, improving efficiency in the manufacturing line. For both these applications, FRAM is the high-performance, non-volatile memory of choice. But speed is only one of FRAM's advantages. FRAM also has very high endurance. Conventional non-volatile memory has limited endurance, the number of read-write cycles possible before the material fatigue kicks in and the memory becomes non-functional. Flash and EEPROM are typically capped at about 100,000 read-write cycles. For flash memory that uses more advanced process nodes, the cap can be as low as about 5,000 cycles. This low endurance translates into short lifespans and means that Flash and EEPROM are not well suited for applications that require frequent data logging. FRAM, on the other hand, has 1 million times the endurance of EEPROM. This makes it appropriate for applications like smart meters that need constant data logging and backup. Here is an example to illustrate FRAM's endurance. Let's say your system needs access to non-volatile memory once every second. With an endurance of 100,000 times, conventional flash memory, or EEPROM, will wear out in less than 2 days. FRAM, on the other hand, will wear out in 317 years or longer. For all practical purposes, FRAM's endurance is infinite. This high endurance makes FRAM ideal for applications where a long memory lifespan is important. FRAM also offers low power operation, about 200 times lower than EEPROM. FRAM runs at CMOS voltages and does not need a power-hungry booster circuit to operate. Fujitsu has also improved the efficiency of its FRAM design, further reducing power consumption. Because FRAM does not need a battery, it is more environmentally friendly than volatile memory. Eliminating the battery also reduces costs and enables a smaller footprint on the printed circuit board. These factors can reduce the production of CO2 during manufacturing by as much as 65%. FRAM is ideal for low-power applications like metering because FRAM consumes little power, does not need a battery, and can safely retain data through many read and write cycles over a long period. Low-power operation makes FRAM appropriate for applications like passive RFID systems, where energy is derived from the external reader or writer. The power-efficient FRAM can extend the effective distance of the passive RFID. All these factors add up to make FRAM the low-power, green memory of choice. FRAM is also very secure. Other non-volatile memories employ the charge accumulation principle, which is like turning transistors on and off to store the ones and zeros of binary data. But this process alters the physical structure of the EEPROM in a way that can be detected using an electron microscope, compromising the security of the data. FRAM does not use the charge accumulation principle. This means conventional analysis with an electron microscope can't detect a change in FRAM's physical structure. This keeps the data secure. Fujitsu has also built-in anti-tampering mechanisms to strengthen security. Upon request, Fujitsu can further enhance the security by combining FRAM with a rich library of crypto engines, as shown here. The result is highly secure products. FRAM security features ensure end-to-end interleave for security locking. This differentiates Fujitsu FRAM from similar offerings. Several of Fujitsu's products are being certified for ISO 15408 EAL4 Plus certification. This is the highest level for consumer applications, equivalent to the e-passports in use today. One example of an application where FRAM is employed for security purposes is the Sony Felica, a popular near-field communication electronic payment solution. Another major advantage of FRAM is its tolerance for radiation. One area where this is particularly important is the medical field. The typical dosage in the medical and pharmaceutical sterilization process is over 20 kilogray. EEPROM cannot survive a dosage of even 2 kilogray, making it completely unsuitable for such sterilization applications. FRAM, on the other hand, can withstand 45 kilogray or more than twice the usual dosage. FRAM can even handle a second irradiation, which is exceedingly rare, without data corruption. Also, FRAM-based RFID has proven to be indispensable due to its radiation-hardened property. There is growing interest in using RFID in the medical industry for anti-counterfeiting measures such as e-pedigree, as well as to enhance patient safety by tracking disposable medical equipment to prevent reuse. Fujitsu's FRAM product line includes standalone FRAM and RFID with FRAM. Customers can also work with Fujitsu to develop custom designs with embedded FRAM. Standalone FRAM, available with SPI, I2C, and parallel interfaces, can be used in any system that requires high-speed, non-volatile memory. Standalone FRAM gives designers the freedom to employ FRAM in a wide range of designs that demand the high performance conventional non-volatile memories cannot provide. RFID is quickly becoming preferred over barcodes to track and maintain audit trails. Conventional RFID uses EEPROM for storage. Replacing EEPROM with high-performance FRAM takes RFID to the next level and opens up applications that are not possible otherwise. This technology is being deployed in various industrial and medical industries. Fujitsu offers FRAM-based RFID with HF and UHF wireless interfaces, and some products also feature an SPI interface. FRAM's affinity to CMOS makes it easy to integrate the technology into existing designs, using current design tools and treating FRAM as a black box. Customers can access the FRAM technology through a flexible engagement model with Fujitsu. The engagement can be a simple foundry model, ASIC, custom design, or anything in between. FRAM combines the best of RAM and ROM. Key features of FRAM include its speed, endurance, low power consumption, security, and tolerance for radiation. These qualities make FRAM perfect for applications like smart cards, RFID, security, metering, and other applications that need high-performance, non-volatile memory. Fujitsu is the pioneer and leader in FRAM technology. The company has shipped billions of FRAM devices over more than a decade. Please contact Fujitsu to learn more about how FRAM can enhance your product design.
Did you ever wonder how could an automatic door function? Or how awesome to use a toilet without the need to pull down the flush? It's always great to have a proximity sensor for you to wash your hand and use the heater. So how does it work? The voltage generator powers the oscillator, which causes the infrared LED to start flashing. The infrared receiver is placed in parallel with the emitter so that it's prevented from detecting the flashing LED. The demodulator blocks every other infrared frequency to disable them from triggering the output. When a person passes, the receiver sees the reflection of the emitted light. This is how the output is triggered.
For this project you will need a 9V battery clip, two 7805 voltage regulator, two N2222 and two N2907 transistors, an infrared receiver and a 555 timer chip, four 1K resistors, two 180 ohm resistors, two 500K pot, 0.1 microfarad, 1.5 nanofarad and 3300 microfarad capacitor, an LED, an infrared LED, one N4007 diode, and of course our 5V relay.
Connect the battery clip to the breadboard. Pin 1 of the regulator should be positive. Pin 2 is related to pin 1 via a 0.1 microfarad capacitor. Don't forget to ground pin 2. Connect the receiver's positive pin to the regulator's pin 3. The receiver's negative pin is to be grounded. Connect the receiver's output to the LED's cathode. The other LED's pin is connected to the two N2907's base via the 1K. Then relate the transistor's emitter to the regulator's output. Till now, the receiver is supposed to function properly. Relay the two N2222's base to the transistor selector using the 180 ohm resistor. Again, don't forget to ground the emitter of the second transistor. You shall now relay the 1K resistor to the first transistor's collector. Then connect in series the 500K pot. The middle pin of the pot should then be grounded. The positive probe of the 3300 microfarad capacitor is related to the base of the 2N2222. The second pin is to be connected to ground. The 2N2222's collector is related to the diode's anode. The relay is added in parallel to the diode and is then connected to the regulator's output. Plug the 7805 regulator. Pin 1 is positive and pin 2 is connected to ground. Pin 8 of the 555 is connected to the output of the regulator and pin 1 is grounded. Connect pin 2 to pin 6. Pin 2 is as well grounded via a 1.5 nanofarad capacitor. Connect pin 4 to pin 8. A 1K should be placed between pin 7 and 8. Another 1K is placed in series with a 500K pot. This pot is then related to pin 6 and 2. Relate pin 3 to a 480 ohm resistor. The infrared LED's anode is connected to the resistor and the cathode is grounded. With a camera, verify if the infrared LED is working, because it can be seen directly by human's eyes. You may need to adjust the spot in order for the oscillation to activate the relay. To do this, place an obstacle between the emitter and the receiver. The adjustment may take a while, so be patient. Now let's use the relay to power on another circuit. We will place in series a battery and a motor. When the switch is activated, the motor should start spinning. Adjust the pot in order to control the switching time of the relay.
If you enjoyed the video, just give me a like, it will help me a lot. And as always, thanks for watching.
If you'd like to learn more about Ferroelectrics, please go to IEEE's frequency control website at www.ieee-uffc.org/ferroelectrics. For more information on electrical engineering, computer science, related science and technologies, please visit IEEE's electronic library at ieee.org/IEEE Explore.